So today we're going to talk about classification, and we're going to cover two very popular and useful classification tools, the logistic regression and random forest. And we'll also talk about different measures to evaluate prediction accuracy, including both the prediction accuracy for continuous outcome and the classification accuracy for categorical outcome. In our case study, we'll again use the data set that we used last time. But this data set doesn't have an outcome variable that has multiple categories. So I included another case study that is not relevant to HIV, but this data set has three categories, three class labels as the outcome variable, so we can use this data set as an illustration for the classification problem with multiple categories. This data set is a data set of different wines. So each entry is a type of wine, and the predictors are the alcohol content and all these different chemical content, all the characteristics of the wine. And we're trying to predict the type of the wine using the chemical and the observing characteristics of the wine. But the majority of the lecture will be focused on the HIV data set. And in this data set, we'll focus on the subset of samples that are, if you unfold the codes, I'm actually using the subset of the data with the measurement of the immune markers, and also I'm only focused on the treated, the patients who are vaccinated. And I want to see among the vaccinated patients, how many of them got the HIV at week 28, and what are the risk factors that are contributing to that. And for this specific data set, we're using the week 20, the HIV status at 28 week as the binary outcome. This is just for illustration purposes. The more appropriate analysis is actually to treat the outcome as a survival outcome, because you're following the patient, you're following up the patient for a period of time. And at week 28, the patient may or may not get HIV, but maybe later the patient will get it. So it's actually a survival outcome, but we are just using it as a binary outcome as an illustration. So in the past lecture, we talked about linear regression, and the intuition for linear regression is to fit a linear plan or a linear straight line that closely depict the data point in the high-dimensional space. But if you have a binary outcome and you make a scatter plot of the observations, it will not make sense to fit a straight line anymore. For example, here, suppose that I'm using HIV at 28 week as the outcome and the IgG level as the predictor. I want to see if this is a good predictor for the infection status. And you can see that I only have two values for the outcome. And if you fit a straight line there, it doesn't really make sense. So what are we going to do? We'll need to, and again here, when we have three racial groups and two values for the outcome, how are we going to describe this relationship using a straight line or a plane? So that's why we need to use something more than linear regression. Specifically, we need to depend on a distribution called binomial distribution. So binomial distribution, in the simplest case, is a flip of coin. You flip a coin and you get a head or a tail, a 0 or a 1. But in our situation, we want to connect this probability of having a tail or having a head. We want to connect this probability with the predictors. So the way to do it is to use a linear combination of the predictors and then wrap it with the function, and then use this thing as the probability of getting a head or a tail. So now you're not completely determining the value of your tail and head using the predictors. You're only determining it up to a probability. So given the age, the risk factors, the IgG level of the patient, you're going to calculate a risk score and then transform this risk score into a probability through a function f. And what function are we going to use for this f? There can be multiple options, but for logistic regression, we're going to use something called the explicit function or logistic function, and the inverse of it is called the logit function. So the mathematical formula is not very intuitive, so I made a plot for those functions. On the left, this is an explicit function. You can see that it's going to transform a real value variable into a variable between 0 and 1. So your linear combination of the predictor, that's going to be this real value thing, and after the transformation, it's going to become a probability. This function is called the explicit function or logistic function. And this is the inverse of that function. It's transforming back the probability to the linear combination of the predictors. So this is how we connect the predictors with the binary outcome. We're not fitting a straight line. We're trying to describe the probability using the predictors. Question? So this is basically the model setting. Yeah.
I may not be.
Mm-hmm.
I may not articulate it, but that's on the mode shape of the explicit function.
Mm-hmm.
Are you saying that you are trying to capture the probability of your outcome falling between the way the initial data was shaped, that you have two extremes?
Yeah.
But the line of continuum.
Right.
In this function.
Right.
Can you explain that or make that?
Sure. So suppose I have a coin. The coin has a probability of having a head that's 0.5. It's a fair coin. So the probability is 0.5. But when you flip it, it's going to give you a head or a tail. So the curve here is the probability. It's not observed. The scatter plot here, this is the head and tail that you observe. So it's a realization of the probability. And this curve, suppose that I have a subject, and after I plug in all the predictor values, I get some value here. And another subject, I get a value that's here. It just means that for this subject, I have a lower probability of observing an infection. It doesn't mean that this subject has to have a 0 for infection. So I may have more subjects that's 0, less on the top, but for this subject, I have, for this area, I have more subjects on the top, less subjects on the bottom. Yeah. So the model setting is actually assuming you are observing a random realization of a probability, and that probability is connected to the predictors. And to interpret so for binomial distribution, there's only one, for 0 and 1 value binomial distribution is also called the Bernoulli distribution. If you flip more coins, you have a multi, your outcome will be 0, 1, 2, all the way to the end. For our case, we're only dealing with binary outcomes. So this special case of binomial distribution is also called Bernoulli distribution, and it only has one parameter, the t. So the expectation of your y, your outcome, is completely determined here. It's just t. And the larger value of this is, the larger value your P is, the more likely you're going to observe a 1. So remember, expectation of Y is P, and down here, I'm going to rewrite it. So P is the expectation of the Y, and if you plug in the X-ray function that connects the predictor values and the probability, it's going to look like this. And you can inverse it and obtain the logit of P equal to the linear combination of the predictors. The reason why we are going through this whole process is because in the interpretation of parameters, if we want to interpret the meaning of theta 1, we need to know what is changing when we change the x1. For example, if I have 2 patients that are all the same but only differ by 1 year old, one is older than the other one, what are the differences in their risk of having infection? So suppose this is the parameter for age. One patient has 1 year old, is 1 year older, then that means that this whole thing for the older patient is going to be beta 1 extra. And that is reflected in the P. And if we look at this whole thing, this is actually the log odds. It's the logit of P, which is also defined as log odds. So what is odds then? The odds is the probability divided by the 1 minus probability. It's monotone to probability. So higher probability also means higher odds. Why we define an extra quantity like this? This is just more commonly used in gambling. So you have the probability of winning over the probability of losing, that's your odds of winning. And when the odds is larger than 1, you are more likely to win. When it's lower than 1, you're more likely to lose. So it's just an alternative to describe how likely an event happens. And if you use the plug in the probability of the infection status as the event here, you will get this whole thing equal to the log of the odds. So here, this is when you plug in there, the probability is this whole thing. 1 minus the probability is this thing. And if you take the ratio of those two, you have the odds, which is P over 1 minus P. That is exactly the exponential of the linear combination of the predictors. And if you take the log on 2 sides, you have the log odds, which is the linear combination of the predictors. Does that connect? So this is our definition. The probability of the event is this x-shaped transformation of the linear equation. And then 1 minus the probability is going to be this value. If you take the ratio of these two, the denominator disappears. You only have the numerator here. And this is the odds. The odds, if you have 2 patients that are only 1 year apart, and the same in the other predictors, you will have the top as the older one, the denominator as the younger one, and you plug in those x's, you will be left with the coefficient for age here. So your coefficient for the age, if you take the exponential value of it, it's also the odds ratio of getting infected when you are 1 year older. So it's not really straightforward. It's not like in linear regression, you have 1 unit increase in X, you have beta unit increase in Y. Now, when you have 1 unit increase in X, you are actually multiplying your chance of getting infected. So
the Xij would be kind of like
age, yeah. So this is 1 year older. So for continuous, like age as a predictor, the odds of getting infected is going to be multiplied by this number if you have 1 unit increase in age. If you have categorical predictors, it's similar as linear regression. Suppose you have we don't have treated versus untreated. Suppose you have like taking vitamin versus not taking vitamin. Then you suppose you are using not taking vitamin as the baseline category. Remember when we construct the categorical variables, you need to choose a reference level. Suppose we choose the not taking vitamin as the baseline and taking vitamin as the value 1 for that dummy variable. Then the coefficient for vitamin will mean that if you change that person from not taking vitamin to taking vitamin, your chance of getting infection is multiplied by the exponential of that coefficient. So every coefficient is interpreted by the exponential of it. It's actually a fold change. That's why sometimes we also say that the beta is the log fold change. It's the fold change of the odds. And so here I have like questions in a cancer scenario. Suppose you have 1 for lung cancer and 0 for no lung cancer as the outcome, and X is smoker indicator, and the coefficient for the smoker indicator is 5. What does it mean? Does it mean that smoking increase your chance of getting lung cancer or decrease your chance? Increase, right? Because if your beta is larger than 0, the exponential of beta will be larger than 1. So it's increasing of the odds.
Does that mean it's 5 times more likely, or no? How would you translate that into how much?
It's actually exponential of 5. So the odds of getting lung cancer is multiplied by exponential of 5. It's not the probability, it's the odds. Yeah.
Can you say, so it's not X, it's tripping me, XI, is it XIL or XI1? That first term.
This one?
Yes.
1.
Is that,
This is the indicator for, this is subscript for the predictors, the first predictor, the J's predictor, and the T's predictor. So we're all focusing on the interpretation of the J's predictor. And the sign of that coefficient corresponds to the direction of the change. It's the same as linear regression. It's just this time it's multiplying the odds. So 0 means the odds doesn't change. The odds ratio is 1. The odds ratio of a smoker over a non-smoker is 1. If you are having a positive coefficient, it means smokers are more likely to have lung cancer. The other way, smokers are less likely to have lung cancer. So in the HIV case, we have the outcome at 28 a week, and then the behavioral risk for the age and the race. This is just an illustration. And you can see the coefficient estimates are here, the p-values are here. And for this specific thing, suppose we're trying to interpret the behavioral risk score, it means that the higher the behavior risk score is, the more likely you're going to get infected. And that fold change on the odds is going to be this number, or 4 times, to have 4 times the odds. And suppose you are trying to interpret one of these categorical predictors. For example, the Hispanic coefficient, even though it's not significant, you can still interpret it. So if you take the exponential value of this thing is 0.7, it means that the odds of a Hispanic patient getting infection, if you take that divided by the odds of a Black patient, it's going to be 0.7. So the odds of Hispanic patient is 70% of the Black patient. And for the inference, you can definitely look at the p-values here, but you need to be careful about if you have a small sample size, because the p-value here uses several approximations behind the stage. It's assuming large sample normality. So you can use it as a preliminary way of looking at which predictors are more significant, but the more accurate test is actually through a likelihood ratio test. This default option is always there because it's just easy to compute, and R just it's super easy for R to calculate it. For the likelihood ratio test, the more accurate one, you have to take your predictor and do the test yourself, so it's not default output. So here, the wall test is the one in here. This is also called the wall type of test. It's just the estimate divided by the standard error compared to the normal distribution. And you have all the formula here. It's just a good like number crunching on your calculator. But for the likelihood ratio test, this is the way of doing it. Like linear regression, we're going to fit a model without the predictors that we want to test for. Suppose we're trying to test for the behavior risk score. We have this model without the behavior risk score. Before we have the model that has the behavior risk score. This is the full model with everything. This is the reduced model without the predictor we want to test for. And then we use the ANOVA function to find the difference between the two models. If they're different enough, we'll say that this predictor is very important. And you need to specify what test you want to use, and the default test in logistic regression is chi-square test. So here, the p-value is actually very close to the wall test p-value because we have a reasonable sample size here. But for small sample sizes, you may find them different. You should always use the likelihood ratio test. And if you want to test for race being useful or not in the prediction, you need to fit a model without the race predictor, and then compare those two. In this ANOVA table, you will see that you are having 2 degrees of freedom, and you are only having 1 p-value. This is not combining the two p-values here. These are 2 individual tests. They are not interesting to us. They're not testing any meaningful things. The meaningful things test for both the entire race categorical variable is not useful. So here I describe more of why we want to use likelihood ratio test instead of wall test. And similarly, for every test, there's a corresponding confidence interval. One-sided test has a one-sided confidence interval. Two-sided test has two-sided confidence interval. Wall test has wall type of interval. Likelihood ratio test also has its own interval. And the wall interval is just easy to calculate one because it's symmetric. It's just your estimate plus minus the quantile and standard error, and it's symmetric. But for likelihood ratio test, it's not symmetric. It's going to need to, you cannot do it yourself at hand. The software will give you that. So by default, if you use the confidence function, you will get if you use the confidence function on the logistic regression outcome, you will get the likelihood ratio test confidence interval. But if you really want the wall interval, you need to use an extra thing in your function head. And this is not going to be symmetric because for the beta that we have, if you have a symmetric confidence interval for beta, then the confidence interval for exponential of beta is actually not symmetric. And we are actually many times interested in the exponential of beta, not the beta itself. For likelihood ratio confidence interval, these are going to be invariant to the transformation. No matter what beta transformation you do, the confidence interval is going to be you just need to do the same transformation on the two ends of the confidence intervals. But for wall test, you cannot do that. So that's another reason why we want to use this. If you want to have an interval for beta, this is it. If you want to have an interval for exponential beta, you just take the exponential for the two ends. Questions? And for prediction, if you plug in the predictor values, you can obtain the predicted probability, or you can transform it into the predicted odds. So we have the predicted probability and the predicted odds, or the predicted log odds. Those are all things that you might be interested in predicting, depending on what you're reporting and which one is easier to interpret. So suppose that we have two subjects with the same behavioral risk score of 1, same race, one is 35, one is 45, then you can construct a new data frame that has this patient in there, age, behavioral risk, and race. And then using predict function, you just need to plug in your new data, your trend logistic regression model here. By default, the predict function is going to give you the log odds, which is this thing. It's just a linear combination of things. It's going to be a real valid one. And if you want to get the probability, you need to let R know you want the type to be response. This time it's going to transform the log odds into the probability for you. So you don't need to do the calculation yourself. So this is exactly like conventional of log odd over 1 plus exponential log odd at the exit function. So now we can say that for a 45-year-old who's Hispanic and behavior risk score is 1, the chance of this patient getting HIV is this is the probability. This output is between 0 and 1. So this is just a point estimation. We're getting a point estimate for this probability. You may wonder, can we get a prediction interval for the probability, like linear regression? The answer is that we don't do that very often. Because first, the interval is generally very large for logistic regression. And then the second reason is that your probability is between 0 and 1. The interval is going to be between 0 and 1. It's really not that helpful. So it's rarely talked about. Any question about the logistic regression, making predictions, doing inferences? So logistic regression can be used to find the association between a predictor and the outcome like we did here. You can look at the table here and find which one is significantly associated, and you can use it to predict the probability of a patient getting infected. You can also use it as a classifier. So instead of getting a probability, you can say that if the probability is larger than 0.5, I'm going to say this patient is infected. In some real world situations, having a probability is not enough. You need to make a decision. Like, do I need to treat this patient or not? Do I need to assign him to some program? So those kind of decisions will require you to dichotomize your probability into 0 and 1. So that is actually a classification problem. Here, suppose that we're going to use age and IgG level for the outcome. This is just for illustration purposes because those two are both continuous predictors and I want to make the plot look prettier. So this is going to be the plot. The color is the outcome, whether they're infected or not. Each dot is one patient. X is the age, Y is the IgG level. And logistic regression is basically trying to look for a linear separation of those data points such that on one side, you're going to classify as infected. On the other side, you're going to classify as uninfected. And where you separate this, how the line is angled is determined by your regression coefficients and where you choose the cutoff probability. So the slope of this line is determined by your regression coefficient. And where the line shift is determined by your cutoff probability. So here I have 3 cutoffs. If you say that the probability, if the probability is above 0.5, then it's a positive case, the line will be here. Because this is a super imbalanced study. You only have very small number of patients getting infected. So your logistic regression classifier will actually predict, your logistic regression will predict almost everyone with a low probability of getting infected. So if everyone's probability is below 0.5 and you draw the 0.5 line here, then you're basically classifying everyone as uninfected. If you choose the cutoff value as the proportion of infected, so that's the green line here. The proportion of infected is about 16% here. So it's saying that if your predicted probability is above 16%, then you're going to be classified as infected. So that's the line here. On this side are all the infected classified, all the patients classified as infected. On the other side are all the patients that are classified as uninfected. And you can choose some other numbers as well. This orange one is 0.2. It's just a random number that I choose. So after you train the logistic regression classifier, logistic regression, you can actually use multiple cutoff values to get the class labels.
I have a question.
Yes.
If we aim for like 0.05
Mm-hmm.
as the cutoff here,
Mm-hmm.
is it possible for it to not be able to generate a line with light effects, or is it always going to, even if that means like having none of the dots? That makes sense?
So your regression coefficients is telling you that when you move from that side, top right to bottom left, you are increasing your chance of getting infected.
Right, okay.
It's just the chance is not high enough for 0.5.
Right, where the line is basically, yeah. The line in the top right corner would be very small.
Right, right. So this is 20%, this is 16%.
Right, and keep going out.
Other questions? So if you don't know which value to choose, I think the safer value will be the average, the proportion of the positive cases. But if you have a really balanced data set, you're safe to use 0.5. So the way to look at where the direction is on the hyperplane is look at the coefficients, the sign of the coefficient. But normally you wouldn't be able to ask to really generate something like this and visualize it. So you only need to know that if you increase the beta 1 here, if your beta 1 is positive, then increase your age will increase your chance. And if you choose different cutoffs, you will have different misclassification rates. If your cutoff is this purple line, your misclassification rate is basically all the positive cases, all the infected patients are wrongly classified. And if you use the green line, then all the blue dots on this side are wrongly classified, all the red on this side are also wrongly classified. So that proportion is called the misclassification rate. Later on, I will also introduce other measures for classification accuracy, but the most straightforward one is the misclassification rate. And for multiple labels, it's also well defined. So it's just if you have a label ABC and you wrongly predict AFC, BFA, those are all wrongly classified, and you just calculate the proportion of wrongly classified samples. That's the most straightforward way of defining classification accuracy. And for our case, if we choose the cutoff 2, which is the mean of the cases, I think. This is the 2x2 table showing you those are the correctly classified ones, and those are the wrongly classified ones. So if you take the proportion of them, it's going to be this number. This is the proportion of wrongly classified samples. If you use the third cutoff, which is 0.2, I believe, then you're going to have changes in each cubicle, and the misclassification rate is going to be different. As you move the line, you're changing the number of misclassified points on each side. If you move the green line all the way down here, you're going to decrease the number of misclassified points on this side, but increase the number of misclassified points on the other side. So the misclassification rate is different. Now, if we have a new patient that has a IgG value of 5 and 35 years old, how do we predict this patient's getting HIV? So it's the same. We're going to use the predict function. This time we use the response. And this is the predictive probability. If your cutoff is 0.2, then you say it's not going to be infected. If your cutoff is 0.16, then you say it's going to be infected. So your choice of the cutoff makes a lot of difference in this classification. I guess this is just a repetition of the cutoff 2. So if you can actually find this patient here. It's 35 and 5, so it's around the line here. And for another patient, without even calculating this number, for example, a 25-year-old with a number of 10 is going to be here. It's classified as uninfected. And if you take another, so this is just like a mental exercise. This is just regressing the binary outcome against one predictor. So what does that mean? Remember we said that the dots are the observed ones. They can only be 0 and 1, and we're going to predict with the probability that's between 0 and 1. So this is our fitted regression line, the estimated probability for each given number of IC level. And you can see that on the right-hand side, you're more likely to have the blue points on the bottom. On the right-hand side, you're more likely to have the red points on the top. So the line is characterizing this trend that you have, more points here and there. And if you want to put a cutoff that's 0.16, this line, it corresponds to this age, this IG level. So it's saying that if your IG level is below the 6, then your probability of getting infected is going to be above 0.16. If your IG level is above 6, the probability is below the threshold, you're going to classify it as infected. So that's just one-dimensional intuitive visualization of what logistic regression does in terms of classification. As far as this classification rate, is there a standard or preferred like range as far as like, oh, well, once you start getting into those numbers, you're really classifying, the classification is just too high. Like, is there a standard, or is it more like, yeah, this is based on your cutoff, this is the acceptable one for what you're doing, and as long as you report it openly, then it's acceptable? That's a great question. So it really depends on how balanced your data set is. For example, in this data set, we have the majority being uninfected. You can just say that I have a nonsense classifier that classifies everyone into uninfected, and the misclassification rate is not going to be very high. It's going to be the proportion of the infected, 16%. So in this situation, 16% is actually the worst you can do. But in another situation, maybe 50%, the flip of coin is the worst you can do. So the reference is how difficult your classification problem is.
But in this case, where you have severely unbalanced categories, you have a lot more of the uninfected than infected. Mm-hmm. Is it still like useful to do this prediction?
This specific data set has very, very weak signal. But in some other cases, you may have something like so you may have something like the majority of uninfected are here, but the infected are here. So this is going to be a super imbalanced data as well, but it's going to have signal. I believe that the conclusion for, well, here we're trying to predict the infection status with two predictors that are not very strong, the age and IgG level. If you do the classification for all of the patients treated versus the vaccinated versus the unvaccinated, the vaccine status is actually very strongly predictive of the outcome. I don't know why the paper says the conclusion is that the vaccine is not effective. But
sorry, in the original paper.
Yeah.
But I was looking at the larger
cohort
group of 1,200.
I see.
People. They didn't really notice.
Yeah. I guess for survival outcomes, they're doing the survival analysis for
Yeah.
That's right.
So was this like a subset?
Yeah.
All the immune data is on a very small subset of the data. I think it's like 189, right? And the whole data set is 1,200 or so. It's over 1,000.
Yeah.
So, and that's where they did effectiveness. But to the point that the trial was actually.
So this is a very noisy case. We don't have a good signal here. There's also trouble when you have a perfect separation of the points. So I'm simulating a toy data example where the outcome is completely determined by X. If your X is below 0, then your outcome is 0. If your X is above 0, then your outcome is 1. So your X completely determines the class label of the subject. And if you do a logistic regression for this thing, this is how I simulate the toy example. And if you look at the regression output, it's actually going to give you a warning, but I think I muted the warning when I made this whole file. But you are going to see a warning. It's going to tell you that something is. Let me show you on R directly. So here are the simulated coefficients, and if you run this model here, it's going to give you a warning message. Algorithm didn't converge. The phased probability numerically 0 or 1 occur. It means that you actually have a perfect separation of the class labels. So when you run into that situation, it means that some combinations of your predictors are completely determining your outcome variable. And it's especially common if you have high dimensional predictors. It doesn't mean that you have a perfect classifier. It may mean that you're actually overfitting your model. So you have so many predictors, useful or not useful, but as long as you have many enough, they can overfit your data and perfectly predict your label. But if you apply this classifier on some testing data, they may actually not give you a good prediction. It's just the large amount of predictors give you an overfitting of the model, the data.
That's how you essentially determine if you're overfitting your model is by just doing a test with like real data or having a test data set to kind of just see how effective that is.
In order to know how overfitting you are, you're right. You need to check how your model performs on an out of sample data set. So that's why when you evaluate the performance of a model, you always use out of sample. You have a training data to train your model, but you have testing data to evaluate your model.
So if this happens, with very few data points, that would make sense. You end up with, all in one group.
Yeah.
But if you have a very large N that happens to match this, can you like kind of filter out based on probability and the N being too small?
You're right that it's also related to sample size. For a large sample size, it's harder to have a prediction. So it's small sample size and large number of predictors in combination that's going to contribute to this kind of situation. So here, this is a two-dimensional example of perfect separation of the labels. And if you run it, it's going to give you the same warning.
This doesn't take into account the size of N at all. Overall, right? The total number of data points doesn't factor in.
So the,
Right, I mean, this would say, you know, with total confidence, every point that lands here is going to be unaffected, like here it's going to be affected. I think that's 100% confidence if the training data is 100%. That makes sense?
so for this specific data set, we are going to say that the misclassification rate is 0.
Right.
Yes.
Okay, and then when you bring in more data to this, or you apply this model to data, it would say, if data point falls in that top left, it would say there's 100% chance that
So if there's another patient that is here,
right.
and I want to predict its color, I'm going to say that the predicted probability for this patient is going to be, it's actually going to be a really, really small value on this side and really, really large value for this
It's
side.
not going to be 100%.
No, because you're predicting a probability.
Right, okay. Gotcha.
Yeah. So the outcome here, I only show you the warning message, but if you look at the coefficient for X is actually super large. You can make it even larger because it's not going to change that plane. It's not converging. Like if you change it even larger, it's going to be the same plane. So if you plug in the value for your X and Y, your X and your predicted Y is actually going to be a probability that's very close to 1. So this is more likely, like you said, you can imagine for a small sample size, it's more likely to happen. And when you have large sample size, it can also happen if your number of predictors has more dimension than the number of patients. It's like you have, remember in linear algebra, if you have enough number of vectors, you can fully describe the low dimensional space you're describing. So if you have 100 subjects and 200 predictors, you can use the 200 predictors to completely represent this 100 dimension space. And that will make this kind of situation happen. Because in high dimensional space, it's super sparse, like the points are everywhere, and you can find a place to cut them through and separate them perfectly.
And it doesn't at any point factor in, they don't factor in that when they then come to conclusion.
No, when logistic regression runs, it doesn't know that. It's just going to plug in every number in that formula and maximize it's estimating using a maximum likelihood estimation. So it's going to choose all possible values of the parameters such that the likelihood of observing your data is maximized. And for this situation, you can just increase your X coefficients no matter how much you increase, the likelihood is already maximizing to 1. So this is the sad scenario of perfect separation. And later on, we'll learn how to deal with the situation where you have more predictors than the number of samples. And for logistic regression, the diagnostics is going to be focused on the outliers because the main model assumption is binomial distribution. Not like normal distribution, you have the normality, you have the samples having the same variation, but here you only have the binomial distribution and there's nothing to diagnose there. So the diagnostic plot is going to be focused on the outliers, and you can use the Cook's distance and the leverage as we did in the linear regression. In this situation, there doesn't seem to be any high leverage point or any high influential point. But if I artificially add one outlier, so here I'm going to add one outlier that is infected, very young, and has a super high level of IgG level. It's not reasonable at all. But I just want to show you how it looks like. If you have such a high IgG level, you shouldn't be infected. But this one is infected, and you can see the influence of this subject is super high here. And the leverage is also high because the majority of the patients have IgG level is probably below 10 or something, around 10, but this is unreasonably high. So when you see things like this, you can go back to your data and check if you have a logging error or is it a outlier that you want to exclude. Sometimes it's just a unit. Some people take the log transformation, some people don't. Some people use the international, like the kilograms, some people just count. And you can try to check which one has the largest Cook's distance, which one is the most influential point, by using the Cook's distance function on the regression output. This is the same, I think, for linear regression. You can identify which subject gives you the highest influential, the high influential point. So that's all the things about logistic regression. Later on, we'll talk about multinomial logistic regression for classification of multiple categories. And then we'll learn how to evaluate prediction accuracy. And the last one is a brief introduction of random forest. Let's take a break of 10 minutes. So this part we're going to talk about multinomial logistic regression. Remember, when you have only two labels, you just need to characterize one probability, right? Because they add up to one. So you just need to characterize the probability of having that positive label. And that is modeled through the probability of one label over the probability of the other label. And this is the exponential of the regression, the regression equation. So this one label positive, that's the negative label. And when you have multiple labels, it's the same logic. You will be choosing one of them as the baseline label and then model the probability of each other label over this baseline label. So here, suppose we have K classes, K categories, and this K is going to be larger than 2. And suppose we choose the first category as the baseline. Then you're going to model the probability of each category over the first category. And this is the odds of J over 1, the Jth class over the first class. This odds is modeled using the exponential transformation of this linear equation. And you will have one set of regression coefficients for J versus 1. You will have another set of coefficients for 2 versus 1, for 3 versus 1. So you actually have multiple sets of regression coefficients. It's going to model the contrast of each label versus the baseline label. And under this model, you can also, so you're modeling J versus 1, but you can actually do the algebra and obtain the equation for example, the 3 versus 2, 4 versus 3. Those can all be obtained. It's just mathematically tedious. And under this model, you can calculate the probability for each label. The first label is the simplest. You only have the denominator. The other labels all have the numerator that's described here. So in this way, you can take the third category versus the second category. You will be having this numerator or each other.
Can you give, I'm trying to distinguish between categories and predictor.
Yeah, right. Yeah, so right now we're having a categorical outcome. Yeah, That's the confusing part. But it's like the categorical predictor, there's the same phenomenon that all categories sum up to one. So if you know, if you have three categories, you only need to know two of them. And when you model a categorical outcome, when you have three labels, you only need to model two of them over the third one. So the number of free parameters is actually k minus 1 multiplied the number of predictors. And logistic regression is a simple, it's just a simple case, a special case of this multinomial regression with only two labels. And this model has a really big assumption. It's the independence of irrelevant alternatives. So because if you're looking at this, it's saying that when I choose between the class category 1 and category J, it has nothing to do with the other categories. So no matter, so suppose I have orange, apple, and banana. The chance of choosing an apple over an orange is going to be independent of the banana. And that may be a very strong assumption, right? When you have a banana, maybe you feel like apple seems more attractive than the orange. When you don't have the banana, you prefer the orange. So those will violate the independence of irrelevant alternatives. But this assumption is a way for statisticians to simplify the world they observe so that they can manage it. And it's a reasonable assumption because most of the times when you choose between two categories, your preference between those two doesn't really depend on a third option. Model estimation is going to be done using this. There are many R packages, but this is a very fast and popular one. So the syntax is going to be the same as logistic regression. You just need to have a multi-category outcome, and it will produce all the similar coefficients for you. So summary of the regression output, you will have one table for the coefficients, one table for the standard error. The reason why we have a matrix for the coefficients is because now we have each predictor here, and this is each category over the first category. This is the second type of line over the first type of line. So if you want to compare so this coefficient is negative. It means that the higher alcohol level is going to be more associated with the category 1 instead of 2. And here, higher alcohol level is going to be associated with category 1 instead of 3. So the sign is still interpreted the same way. It's just how you interpret the odds is a little tricky. So if you exponential this number, it's going to be the odds of 2 over 1, the odds ratio of 2 over 1. And this is the exponential of it. It's going to be the ratio of odds for 3 over 1. Does that make sense? And then you have the standard errors to help you do that simple wall test. I don't believe I have the code for testing each coefficient. That's also feasible through the likelihood ratio test with the likelihood ratio test. And I think for classification, most of the people are more interested in like getting the label right. If I have these characteristics of the line, which type of line should I classify it into? For that task, you can use the predict function again. And there are two ways to do the prediction. One is to obtain the probability, and one is to obtain the label. So this is by default, this option will give you the probability. I'm just rounding the number so it's easier for your eyes. And you can see that the first line is having a big probability here. And the third one has the biggest probability here. Each row sum up to 1. So this is how you're going to predict each one falling into each category. And most of the times you would choose the category with the largest probability. Instead of when you have two categories, it's like you have more wiggle room, but when you have more categories, it's mostly just the majority vote.
Quick question.
Yes.
So when you build the model, or choose type, will it automatically just pick number 1 or whatever is number 1 in the order? Or do you have to specify if you want it?
Oh yeah, it's the same as the categorical predictor. So by default, it's going to, if you're having a factor level, it's going to choose the first level. If it's character variable, it's going to alphabetically rank the first. Yeah. But you can specify that yourself. And if you want to do the classification, you just choose the largest probability, and that is done using the default predict. So if you don't specify type equals probability, it's going to give you the label prediction. And this table function is one of my favorite R functions. It's going to tabulate the observed labels and the predicted labels. And on the diagonal, you have the correct ones. All diagonals are the misclassified ones. This is also called a confusion matrix. So if suppose we have a new one that has this level of alcohol level and this level for the color, you can plug into the regression coefficient. So plug in those numbers, you will get the log odds for each category, and then transform them into probabilities. You will have these numbers. So fortunately, you're not my undergraduate students who have to do that by hand. But then you can just use the predict function, type equal to probability, and you will know that it's more likely to be a type 2 one.
So scroll up a little, that shows all of the 10 different lines dimensions to the.
So these are 10 wines.
10 wines.
Yes.
Oh, okay. 1, 2, and 3 were the categories of types of wine.
Right, these columns are the types of wine. So for each wine, I'm predicting the probability of falling into the 3 categories. For this specific data example, this is how you do it hand calculation. But you can see that this number, when it's negative, is directly reflected into the probability here. It means that increasing the alcohol level will put it more likely to be a type 1 wine. And then you can obtain the log odds for each category. So now you have the probabilities. If you want to calculate the odds ratios, you can take the ratio for each pair of them. Take the log, you have the log ratio, odds ratio, and they are actually correspond to these regression coefficients. So for this specific example, when we have 2 predictors and 3 labels, it has a very nice visualization. So each point is one observation, one wine, one label of one brand of wine, and each color is one type. The logistic regression, the multinomial logistic regression, is actually going to draw 3 straight lines. One line is for 2 versus 1. One is for 3 versus 1. One is for 3 versus 2. And Using those three lines, you are going to divide the whole space into 3 parts. And each part corresponds to one label. So if you look at this straight line here, it's comparing the probability of 2 versus 1, the odds of 2 versus 1. So on the right, you're more likely to be 1. On the left, you're more likely to be 2. And then for the dotted line here, this is 3 versus 2. On the bottom, you're more likely to be 2. On the top, you're more likely to be 3. For the dashed line on the right-hand side, you're more likely to be type 1. On the left, you're more likely to be type 3. And combining all of those, so if you look at each point on this plane, you will have a probability for each category. And the color of that plane demonstrate which category has a larger probability. Any questions? So this is one way of doing multinomial classification. Here, the type 1, 2, 3, they don't have an order. In some other situations, you may have a natural order, like your response is cancer outcome that is stable, progressive, or clear. Like you have I think they have three labels. You have getting worse, getting better, and stable. So those have a natural order, and using this may not be the best option. You can still use it, but if you want to have a model that accounts for this order, there's a slightly different version of multinomial regression that's called the ordinal multinomial regression, but we're not going to cover it here. Any questions? So evaluating prediction accuracy, we have last time when I talk about linear regression, I should have included this quantification for prediction accuracy for a continuous outcome. Basically, you have three basic, very intuitive measures that are quite popular. The first one is mean squared error. This one is the most used one. It's simple and it actually corresponds to the linear regression very well, because linear regression is trying to minimize this. So a mean square error is a natural criteria for the goodness fit of linear regression. But people use it for other regression models as well, as long as you have linear outcome. It's measuring the difference but squared and then summed up. And if you remember the shape of the x squared function, it's actually going to go up really quickly. So this thing emphasizes a lot on the bigger values. If you have a point that is very wrongly predicted, it's going to have big impact on the MSE. On the other hand, the mean absolute error, this thing is not taking a square, it's just taking an absolute value. So the shape of absolute value is like this. The shape of square is like this. So the squared curve emphasizes more on the larger value. The absolute value is going to treat everyone similarly. So the mean absolute error, this criteria emphasizes less on the outliers if you want this to be a criteria for your evaluation. And then there's the variance extent. This quantity is very tempting because for these two, they do not have a range that you say, hey, if mean square error is this number, then it's small, because it depends on the scaling of the response. If you use kilograms, it's one value. If you use pounds, it's another value. So there's really no standard value to compare this with. But for R square, it's really tempting because it falls between 0 and 1. And when you see a larger R square, you would you tend to think that your model is doing a good job. But this is very misleading. I've seen a lot of people arguing against the usage of R-square. I think it's just necessary for people to realize the limitation of R-square. And I named two major ones here. You can search for some online blogs and they will talk about other reasons for not using R-square. R-square is defined as the total sum of squares and the residual sum of squares. So it's the residual sum of squares over the total sum of squares. This is just similar to the residual sum of squares is just similar to the MSE, the mean square error. It's just without the n. So the difference between this R square and mean square error is mainly that you're dividing it by the total sum of squares. So what difference does it make? First, it makes it between 0 and 1, but it also disables you from using it for a new sample. When you have a new sample, you can calculate the numerator. You can calculate the difference between the observed value and your predicted value, but you cannot calculate the sum of square total because this is based on the training data, not the testing data. So I think this is a lethal, like a prohibiting reason for me to not use R square because it doesn't really quantify the out of sample prediction error. And it's the out of sample prediction error that's more objective. That's free from the overfitting problem. And then if you have the model that performs if you have a regression line that has the same prediction accuracy for all of the y's, suppose the difference between observed y and the predicted y is the same, that you have the same amount of prediction error for all of the y's. And if you narrow down to a small range of y, you will have a smaller number of SS total. If you look at a larger range of y, you will have a larger SS total, but your SS residue is the same. So in these two situations, you actually have the prediction accuracy that's the same, just because the range of y you're looking is different. You have a larger R square in one case and a small R square in the other case. So it's quite misleading. And also R square doesn't tell you whether your model is wrong or right. R square characterizes a linear relationship between y and x. So, but in many of the situations, when you have a nonlinear relationship, it can still give you a large R square. So here I have two examples. This first example, I simulated the data using exactly the linear model. Y is x plus some noise, but because the noise is very large, you can hardly see the linear relationship here. And if you calculate the R square, it's quite small. It's only 13%. But this model is correct. In this example, I'm generating a wrong model. That's a square term. So y is x plus 2 squared plus some noise. This is definitely not a linear regression assumption. But if you fit a linear regression to this data, you will have a really high R square. It's 80-something%. You can visually see this is not a linear model, but you have an R square that's large. So R square doesn't really tell you whether your model is right or wrong. Any questions? So in general, I would caution against using R square for overstretching interpretations. And I think another argument that I've seen is that people say that when the R square, for example, here, R square is, in this example, R square is 13%. So it's saying that 13% of the variance in Y is explained by X. But if you do a reverse regression of X on the left and Y on the right, you will have the same R square. So does it mean that your variance in X is also explained in Y? There's really no direction of which explained which. So in reality, you barely know where the causal direction is. These models help you with the association analysis, but you barely know which one explain the variation in the other one. So most of the machine learning models, you will see them using the mean square error as the evaluation for model accuracy. For categorical outcome, this is a bigger story. So let's just focus on the two categories. Because when we have multiple categories, misclassification is the one that we use. That is straightforward. But for two categories, there are different ways of characterizing how accurate we are. The first one is, so in this table, I have rows for the observed label and the columns for the predicted label. It's very similar to the hypothesis testing type 1, type 2 error thing. So here you have the diagonals that are true positive and true negative correctly classified. Those are the wrongly classified. And in the classification accuracy framework, you would define the misclassification rate as the off diagonal elements over the total. That's the percentage of wrongly classified points. And then false positive rate is B over A plus B. It is the proportion of the falsely classified points among all the negative cases, all the zero cases. That's the false positive rate. And false negative rate is the false labels, the falsely classified ones among all the positive cases, all the one cases. The denominator is going to be given. The denominator doesn't depend on your classifier. It's the numerator that depends on the classifier. So for logistic regression, when you move that line across that plane for different cutoff values, this A plus B is not going to change. This C plus D is not going to change because those are the number of observed zeros. This is the number of observed ones. When you change the cutoff, the B and C will change. One of them will increase and the other one will decrease. There's a trade-off between those two. So when you choose the cutoff value, you would want to choose somewhere where the B and C are both reasonably small. And the false negative rate has another name. If you take 1 minus the false negative rate, it's also called recall or sensitivity. It's just different people from different fields giving different names. And for specificity, it's 1 minus the false positive rate. So when you have a trade-off between the false positive rate and false negative rate, you have the same trade-off between sensitivity and specificity. It's just the 1 minus of each of those two. And there's another pair of criteria that's precision and recall. Recall is the same as sensitivity, but precision is not the same as specificity. It is going to be having a different denominator. So the denominator here is B plus D. It's the proportion of all the ones that you predicted as one. So when you shift that regression line in the plane, this B plus D will change. So there's, when you shift that line, the sensitivity and specificity, those are going to move monotonically, but precision will not. It may go back and forward. Recall, precision, and recall and sensitivity and specificity is going to move monotonically when you change the cutoff. And this is also one of my most visited webpage. It has this huge table of all the different names people give to the 2x2 classifications. It's just really confusing, so I look it up all the time. And I have to zoom in again. We talk about the trade-off between sensitivity and specificity, and for precision recall, there's a similar trade-off, but it's not really monotone. And you also probably already heard about the ROC curve and precision recall curve, right? So the ROC curve is plotting the sensitivity against specificity, or 1 minus specificity. So here we have one example of the ROC curve for the logistic regression classifier that we have. This is model somewhere, I forgot. But for that model, we are predicting the infection status. And on the x-axis, we have 1 minus specificity. On the y, you have the sensitivity. And this curve is going to have a larger area under it if you have a better classifier. So as you move the cutoff value from very conservative to very liberal, you will have more patients classified as infected. And the more you classify people into infected, the more sensitivity you have, but you will lose specificity. So that's the increasing trend here. And for a good classifier, it may look like this, because you don't have to lose a lot of specificity to get a good sensitivity. So when you have a really bad classifier, that's the straight line here, that's like the worst you can do, then you would have to lose a lot of specificity to get the same increase of sensitivity. That's why we want larger area and that means better classifier. So the ROC curve, the area under it is going to be 0.5. If you have a useless classifier, we'll give you an example of the useless classifier later to tell you why it's 0.5. And if you have a perfect classifier, then it's going to be 1. So you will have 0, you will have a specificity of 1 and a sensitivity of 1 here. You will have a value here that's characterizing the ROC curve. And the ROC curve compared to the precision recall curve that we will talk about later, is going to treat the positive cases and the negative cases equally. So if you revert the label, if you change 0 into 1 and 1 into 0 for your outcome, it's going to give you the same result. You train the logistic regression, it's going to give you the same result and same ROC curve, same area under the curve. One drawback for ROC curve is that it may be overly optimistic for imbalanced data set. In our situation, it's not overly optimistic, but for this situation where I draw, so it has the negative case everywhere. That's the majority, but the positive case is going to take a small corner of that thing. In this situation, you are going to do a very good job classifying the negative cases. The misclassification is going to be very low because you're just misclassifying the ones that overlap with the positive ones. But when you look at the positive cases, you are going to do a poor job classifying them, because you cannot really tell the difference between these positive cases and the other negative cases around it. So in this imbalanced data set, if you calculate the ROC curve, it's going to give you a very large area under the curve, because you do a very good job for the negative cases. So that's why you shouldn't be overly confident about your ROC, the area under the curve of ROC if you have very imbalanced data set, because that may just mean that you did well in one class but not the other. But on the other hand, the precision recall curve is going to emphasize one class. You are going to choose which class you want to emphasize on. So it's not treating zeros and ones the same. Here is an example of the precision recall curve. So the jump here is mostly due to the imbalance data set that we have. So for the very left, you have a very low sensitivity, but a high precision because we're basically classifying everyone as not infected. Classifying everyone as uninfected is going to be quite precise, but it has a very low sensitivity, right? The area under this precision recall curve is also the larger the better. When you have normally it's more of a monotone shape, but because the precision is not increasing monotonely as you change the cutoff, you may see some wiggling here. But it's the larger the better. And it's going to be compared to, instead of compared to 0.5, you're going to compare to the proportion of positive cases. So the worst you can do is not 0.5 for the area under the curve. It's the prevalence of your positive cases. In this case, it's going to be 0.16. Oh, sorry, it's the 0.2. No, it's 0.16. I think that's 0.16. Yeah, 0.16. So the precision recall curve is going to emphasize on the positive cases. So suppose you want to do a good job for the infection, the positive ones, then you would want to put the infected ones as 1 and uninfected 0. But if you want to do a good job to classifying the uninfected ones, you would reverse the 0 and 1, and you will have a different area under the precision recall. So it's possible that you have two classifiers. Classifier A has a larger area under the curve for precision recall if you use label 1 versus 0. And the other classifier may be better if you reverse the label. The two classifier may do different jobs on classifying each class. And the precision recall is going to capture that. It's going to emphasize on the label 1.
What is the best you can do for precision?
The best you can do for precision recall, the area under the curve? That's a good question. Is it 1? I think it's 1. Yes. So you can have a sensitivity that's 1 and precision that's also 1.
I think all of them are close.
Sensitivity.
Point they don't have it.
So if they are both 1, then C and B are both 0. C and B are both 0, so you're having a perfect classifier. When you have a perfect classifier, C and B are 0, so sensitivity is 1, precision is 1, everyone is 1.
Yeah, I've never seen it that high in practice.
Right, it's just a special case.
Yeah, and like the AUC, I feel like you'll see like the AUC be really high. Precision recall curve sometimes just be small. Especially for like rare cases.
Yeah, because you are benchmarking against the prevalence of the positive case.
It's always fun to do like a publication like where they have like very small outcome groups, like they'll have a very high AUC, but they won't report the PR.
Right.
So that's gonna be your big red flag when you're reading.
Like yeah, it's just something to think about.
Yeah, it may be a situation like this. It's not like super bad, but it's not even a good job for one group of people.
So that's kind of, so especially if you're in practice, like looking at different research to see what's going on, when you find something that's kind of a red flag, it's like, let me keep searching.
Yeah,
Let me keep
yeah,
expanding that literature search, just to kind of see what other research is doing.
yeah. So that's why machine learning people mostly recommend precision recall curve for the imbalance data set. You see ROC more often so in medical research. So there are two ways of getting the ROC curve. One simple way is just this PROC package, and you do the ROC function on the observed labels and the predicted probability. I think this is the most simple way that people love. And if you do the plot of that ROC curve, you can ask it to print the ROC, the AOC, and shade the area under it. It's really nice. But if you want to get the precision recall curve, you have to use another package. And that package is a little cumbersome. This is the package, and you have to make sure you put in the right order so that you know which one is treated, is emphasized on. So this is emphasized on the positive cases. You have to do it the other way if you emphasize on the negative cases. You don't have to fit the regression model twice, but you by reversing those orders, it's a little tricky. But this is a good way to check whether you are making them right by comparing this version of ROC with this version of ROC. If you get them matched, then you can change the ROC function into PR function. That gives you the precision recall. So here, you just need to change the ROC into PR. And this is how you extract the value for the precision recall area under the curve. And now let's look at what will happen if you have a poor classifier that basically is doing nothing. So this classifier is not informative. It's going to take the same proportion among the zeros as predicted. So among the negative cases is going to predict Q proportion of them as 1. Among the positive cases is going to predict the same proportion as 1. So it's doing nothing, it's predicting everything with the same proportion. And you can change that proportion from 0 to 1. So this is the number of negative cases, this is the number of positive cases, and the predicted value is going to be negative multiplied by this proportion, and positive is this proportion, so and multiplied by my classifier's performance. This is P multiplied by my classifier's performance. And if you plot them in, the sensitivity is going to be D over this row, so it's going to be exactly Q. And specificity is going to be 1 minus Q. It's this number over this number. So you will have sensitivity equal to 1 minus specificity. That's exactly that line, straight line you have, the diagonal one. And for precision, it's going to be this number over the column sum is actually going to be P over P plus N. That's the proportion of positive cases. So you're going to have a precision recall curve that's a flat line. It's always going to be this number. So your ROC curve is a straight line, and your PR curve is going to be a flat line. And the area under this is 0.5. The area under this is going to be the proportion of positive cases. That's the most useless classifier you can get. And if you do worse than this, it means you're really overfitting. I've seen ROC and area under the ROC curve that's smaller than 0.5. It's mostly because you're overfitting. So you're overfitting your training data such that when you're predicting on your testing data, you're doing a worse job than a meaningless classifier. Does that make sense to anyone? When I was teaching the undergrad, I was trying to describe this overfitting problem as a close fitting scenario. So suppose that I want a suit fitted for my husband. I can measure all the places like arms, shoulder, chest, everywhere, or I can just take a few major measurements. So if I take the measurements everywhere, it's more like I'm fitting the data with a highly complicated model with multiple predictors. When I only measure a few places, 3 places like shoulder, waist, and chest, then it's a small model. It's a simpler model with fewer predictors. And I may do a very good job fitting this suit on my husband. But if I put this suit on a different person that's the same height, similar shape as my husband, it may not fit him well if I overfit my husband. So the suit fits well for my training data, my husband, but doesn't fit for a general population. And when you design a suit for a large mass production, you don't want it to overfit one specific person. If you want to train a model that's predictive of a larger population, you don't want it to be overtrained using your training data.
So that means you need to be selective about your predictors.
Right. So that means that when you when you evaluate how well you fit that person, you need to evaluate using your testing data.
Is there like an ideal number for studies like this where you have like so many predictors? Is there like an ideal number of predictors you can shoot for?
The number of predictors you can use is strongly affected by your sample size. When you have like the IT companies, they have the web page click data, they have millions of entries. In those situations, they can afford millions of predictors. They don't really care about the interpretations, they just care about the prediction, and they don't mind using thousands of predictors. But in medical research, your sample size is barely in the millions. And you want to have interpretation of each predictor. You want to know which are the risk factors, which are the things that I need to watch out for in the future. So in that situation, you would want a smaller model. I guess, does that answer your question? Yeah, there's really no ideal number of predictors. But
I mean, you know, in this case where you don't have a lot of like you have limited sample sizes. My question is, how do you address the question of overfitting?
yeah.
You just try, several different numbers of predictors and then pick a sweet spot, say 5 predictors work better than 6.
Right. So next lecture, we're going to talk about something called cross-validation. It's going to use training data to train 3 models and then evaluate those 3 models on the testing data and see which of the models perform better on the testing data, and that's the model you are going to choose.
Yeah, I forgot about the model.
Yeah. Well, different set of parameters also means different models. You can think of that way. So here I also just throw in the case where I predict everyone with the same probability. And if you calculate the ROC area under the curve and the precision, recall area under the curve is the same as that classifier that you have. So this is the worst you can do.
So 0.5 is the worst.
For ROC. Yeah, for precision recall, sometimes you see a very small number and you get frustrated, but it's still much better than the worst you can do, then it's still worth reporting. Yeah, so I guess we'll take another break and then talk about random forest. It's a long lecture today. So for the remaining of today, we're going to talk about random forest, a fancy concept that's super helpful in many of the situations. The random forest is a forest of trees, and each tree is a decision tree. A decision tree can be a classification tree if you have a categorical outcome, or a regression tree if you have a continuous outcome. They're both decision trees. And here I have a small toy example of a decision tree. So each tree node will have two splits, yes or no. And each tree node will include one predictor. For example, here I'm trying to check this continuous variable is larger than 6 or not. Yes, then go here and then do another split. No, the entire data set will go through this tree from top to bottom, and then all of the samples will fall in each of those orange boxes. And the decision tree will predict the label for each box using the majority vote. So if I have more cases, more infected in this subset of patients who have yes to drug usage, yes to more than 0 partners, yes to 30 years old, and yes to IgG level larger than 6, this subset of patients, if the proportion of infected is larger than 0.5, I'm going to predict it with 1. Otherwise, it's 0. So the entire space of samples is actually partitioned into these boxes according to the value of the predictors in each node. And each partition is going to be given a label based on how many cases are there. This is a classification tree. If you have a regression tree, you're still going to do the same partition for your space of samples. Instead of getting a label for each partition, you're going to get a mean value of the outcome for each partition. So the only difference is whether you're averaging the continuous outcome in each partition or using the majority vote of the labels in each partition. And you don't have to have binary outcomes. You can have multiple labels, it's going to be the same. So it can be predicted with A, B, and C in the leaf nodes. The classification tree will make the prediction for each leaf node inside. It's not going to make any predictions, but it's going to find the split that gives you the best tree. So what do we mean by best tree? Let me show you a small toy example for just one tree node split. Suppose that we start with this whole data set. There are 25 infected and 125 uninfected. And we're going to evaluate how impure this set of subject is using the Gini impurity. It's calculated as 1 minus the summation of each proportion squared. So this is going to be a different number if you have a different distribution of the infected and uninfected. So here we have 16% and 83%, and the Gini impurity is this number. Suppose we have 0.5 and 0.5, then it's going to be 1 minus 0.5 square minus 0.5 square again. And let's see how large that is. That's going to be the most impure you can get. That's the 0.5. And if you have all of them in one label and none of them in the other label, it's going to be the most pure. It's going to be 1 minus 1 square, which is 0. So the larger value it is, the more evenly distributed of the sample between the two labels. And you would want to make it larger or smaller when you split the trees. you want it to be smaller because you want them one leaf node to only have one label. So for each split of the tree node, we're going to explore all of the predictors. And for continuous predictors, you're going to explore all the cutoffs. For age, you're going to search the age range and find the cutoff that gives you the best split. And for all of the predictors, you're going to randomly choose one of them and see how much you can decrease the Gini impurity. So in this specific case, let's look at age larger than 30 as the cutoff. After you split the node, you have this number of infected and uninfected in each node. And the Gini impurity is going to be calculated for each node and then weighted combined. And that number is going to be this. For this split, the number is 0.26. So apparently this one has a bigger decrease of the Gini impurity. Between those two, which tree split you would choose? On the right. So for each split of the tree, you just keep growing. You keep explore all of the predictors and grow the trees, and you stop when you reach the minimum number of samples for each leaf node. So when your leaf node has only maybe 1% of the infected or 1% of the uninfected, you don't have to split that node anymore. Or if you reach the total number, if you split the tree and it's not going to decrease the impurity by much, or if you split you already reached the tree is pretty tall, and that's also a place where you can stop. For this specific toy example, we're using classification as an illustration for the tree node split. If you have a continuous outcome, you will not calculate the Gini impurity. Instead, you will calculate the mean square error. So for each node, you're going to have maybe like a continuous distribution of the outcome, and then you will calculate how much variance it is in this node, how much variance is there in this node, and how much variance is there in the parent node. If you do a good split, then the variance plus this one variance should be smaller than this variance.
You're talking about building a tree with you. Do you mean that first you check if the age is greater than 30, and then on the next box you check IHID plus pot, or yes or no, like this is all going to be one tree? Or is this testing a bunch of separate trees in just one?
This is one step of growing a tree. When you grow the tree, you need to make a decision on what variable to use for each node, if you have a continuous variable, what cutoff it is. But when you choose this, your samples will naturally be split into two parts. When you already choose this variable and this cutoff, then your samples just they start sitting in a row like this. And
so when you talk about building, maybe you take this individual new sample and you pass it over that first node, right? And then maybe pass it over the next node, give you more accuracy.
Yeah. So the more you split, this is 150 samples, and you split them, and this is probably 10, this is 20. Have like a subset of samples in each leaf node. And you may stop growing in the middle because you may reach the smallest number of cases. For this example, has gonorrhea is all of the patients having gonorrhea are positive cases. So you don't have to do I actually use one. So you have a perfect predictor there. You don't have to grow the tree here. So for categorical ones, you calculate the Gini impurity and see whether you can get a big decrease. For continuous outcome, you are going to calculate the MSE for the parent node, and then calculate the MSE for the child node. So this is like the spread of the left node. This is the spread of the right node, and this is the spread of all of them combined together. If you have a good separation of the two nodes, you should have a smaller sum here compared to the original spread. So it's basically like this. You have the pen is not working. You have one set of points here, one set of points here. You calculate the spread all combined. This is big, but if you do a good job separating those two and do a spread here and spread here and sum those two up, it's going to be smaller than combining the two groups together. So the good split will give you a big drop in the MSE. That's for continuous outcome. A lot of people think that regression forest random forest can only be used for classification, but the truth is it can also be used for continuous outcome. Pretty powerful. After a tree is built, if you have a new sample, you can get the predicted value for that sample by passing that sample through the tree, and then you will predict with either the majority of the label if you have a classification, or you will predict with the mean of all the samples within the same leaf node. So the prediction is made using all the samples falling in the same leaf node. Does that make sense? So this is just doing one tree. The power of random forest is that it's going to use many trees. And how do we get many trees? It's by drawing a random subset of the samples. When you do a different subset of samples, you will likely, your optimal tree growing will probably be different for different subset of samples. This process of drawing a subset of samples for training is called, the resampling is with replacement. This is called bagging, and the samples you leave out of the bag is called the out of bag samples, and those are good for evaluating prediction accuracy. So the entire random forest growing process is already incorporating training and testing inside it. Unlike logistic regression that trains the model on all of the samples, the random forest inherently split the samples into training and testing in there. So it suffers less from the overfitting problem. And when you have multiple trees, one tree may not do a good job, but when you have a lot of trees averaging together, you actually decrease the prediction variance, and that's really increases the accuracy. And if you just randomly choose the samples and not randomly choosing the predictors and just grow the optimal tree for each random sample, it's called a bagging. It's not exactly random forest. For random forest, you also have your random component that is randomly drawing a set of predictors for each split of the tree. The benefit of doing this is that for each split of the tree, you're not trying to optimize among all of the predictors. You're choosing a subset of the predictors. So even your weakest performing predictors may have its chance. Suppose you have two predictors that are strongly correlated, but one is always doing much better than the other one. Without this random without this random component, you will always build a tree with a stronger predictor. But with this random component here, in some of the tree building, you may use the second best predictors. So all of the predictors have their chance to participate in building the forest. And you prevent a single strong predictor from dominating all of the trees or maybe overfitting the data set. Compared to logistic regression, the advantage of random forest is that first, it can characterize nonlinear predictor outcome relationships. So when you're building a decision tree, there's really no monotonity in there. For this tree, you may have an age split at 30. For the other tree, you may have age split at 25. For this tree, you may have age before number of partners. The other tree may have the other order. So there's really no well-defined connection between the outcome and the predictor. The good thing is that you can characterize all kinds of nonlinear relationships. The bad thing is that you don't really have a defined relationship, so you don't know where the direction of effect is. So that's the advantage versus the disadvantage. You can characterize nonlinear relationships. You can also handle very complicated interaction effects. You don't have to explicitly model the interaction effects in the random forest. In logistic regression, you have to put the interaction term in there to model it. But for random forest, you don't have to. They will model that for you. The disadvantage is the interpretability. You don't know the direction of effect. You don't have the effect size. And you don't know whether the relationship is linear or quadratic or anything. The advantage over logistic regression is that it's more robust to outliers because you're doing a random subset of samples for each tree. So your outlier will have a smaller chance of affecting all of the trees. And it can handle more predictors than the number of samples. In logistic regression, you have to have more samples than the number of predictors for the degree of freedom. But for random forest, you can start with whatever number of predictors, and they may be collinear. They may outnumber the number of samples by a large amount. But as long as you define your tree depth, the number of splits, all those hyperparameters in the tree well, you will be able to fit it. And the downside is that if you do have a linear relationship between the predictor and outcome, you may actually find a better performance in logistic regression. I've had that situation in some of the case studies I've done. So sometimes you just have a very simple relationship, and running random forest is overkill. It's actually going to give you a lower prediction accuracy. And also random forest can be more computationally expensive if you have a large data set. And there are several hyperparameters in the tree that you can tune. The number of trees, this is by default set to 500. It's the number of subset of samples, resampling of samples you do. Your forest will contain 500 number of trees. If you have a large data set, you may want to make it smaller because it saves time. Smaller forest saves time, but you cannot make it too small. You have to give each sample a chance to participate in the tree building. The node size is the minimum number of samples to be present at each leaf node. So you don't want it to be too small so that the prediction for that leaf is unstable. And there's a default number for R as well. If you set it to be a larger one, then you have a more stable leaf node prediction, but your tree will be smaller. There's no guarantee whether a larger one or a smaller one will give you a better prediction performance. Those are the parameters that you can play a little bit and see if it can help you increase the prediction performance. And M-try is the number of predictors to randomly sample for each split. If you have a large number of predictors and many of them are strongly correlated, you may want to choose a smaller number for this. There's also a default number in R if you want to use that. So those tuning parameters, most of the people don't really check them. But there's one thing in in the setting of random forest, you need to be careful about which is the stratified sample layer. If you have a very imbalanced data set, remember this node will do the prediction based on majority vote or the average of everyone. If you have a very imbalanced data set, if you only have a few infected patients and majority are uninfected, the majority in all of the leaf may be uninfected, and you may predict everything with infection. So if that is something that you don't want, you would set the stratified sampling here. I have the code for running random forest without stratified sampling. In this specific case, I'm using these 3 variables plus all of the behavior risk variables to predict the infection outcome. This is like 30-something predictors. And you can see for all of them, the tree is predicting them to be uninfected. The forest is doing this. But if you do it with strata, this is how you do it. You first specify that the strata variable is the outcome variable. You want to stratify based on infected or uninfected. So the stratified sampling means that when you randomly choose a subset of samples to build a tree, you try to make your subset of samples balance between the case and the uninfected. So here I'm specifying for each randomly generated sample set, I want 30 to be uninfected and 15 to be infected. And this is telling R to generate the feature importance score. We'll talk about that later. But this is how you specify it. Because we have a very small number of cases, I think it was 25. You don't want this number to be too close to 25, because in that case, you're not really doing resampling of the cases. And you try to make these two closer to each other because you want your training data for each tree to be balanced between the case and control. So these two numbers, you can specify them yourself depending on how much sample you have.
Or if you make both of them the same, 15 and 16.
You can do that, yeah. It's just the
number of
yeah, yeah, right. You can tweak that, but if I change it into stratified sampling, at least I'm classifying some people into the cases. The overall estimation error, this is the out-of-bag prediction accuracy, the misclassification rate, this is higher than this. Because the best classifier should just classify everyone into uninfected. But if you don't care that much about the uninfected and you want to do a better job doing the classifying the infected ones, then this is a better classifier than the previous one. So misclassification rate is unbiased between the two cases. If you want to emphasize on one of them, you shouldn't rely on this number. And for the wine data, it's more balanced, and the signal is also very strong. If you run a random forest on the diagonal, these are the correctly classified ones. You only have 3 samples that are misclassified. And just as an illustration, I'm running a case study to the wine data example with one of the variables as continuous outcome. I'm trying to predict the alcohol content with all the other features of the wine. So, oh, sorry. This is an example to let you know that you need to make sure R uses your categorical variable as categorical variable. So here, the type of wine is 1, 2, 3. If you don't specify it as a factor variable, if it is read in as a numerical variable, it will run a regression tree instead of a classification tree. So make sure you let R know your outcome is continuous or categorical, because they can run, random forest can run both. It will not be an error message for you. But from the output, you can see whether it's a regression tree or a classification tree. If you see mean square error residue, this is a regression tree. This is a forest from regression tree. And if you see confusion matrix, this is a forest from classification tree. And to do prediction for classification trees, like we said, we're going to use the majority vote for the corresponding leaf node. And you can obtain that using the predict function again, have equal to response for the random forest outcome. I'm just taking a subset of the samples to show you how the predicted labels correspond to the predicted probability. So here, this gets to the labels, this gets to the probabilities. Same as the multinomial logistic regression, you're going to use the largest probability for the labels. So the first 5 ones all have largest probability in type 1, they're all given level 1. And you can obtain the confusion matrix from classification using this dollar sign confusion, and it will help you understand which category is it doing well and which category is it doing worse. For regression trees, instead of taking the majority vote for the members in that leaf node, you're going to take the average of all the samples in the same leaf node as the predicted value. So this is running a random forest trying to predict the alcohol content using all the other wine features. And it's reporting this variance explained. You can do that for the same sub. I guess you can do that. You can compare the variance explained for the same set of samples. And the larger variance explained means a better prediction accuracy, but variance explained compared across different data sets is not meaningful. And if you want, so up until now we're talking about prediction, but if you want to know which predictor contributes more, then it's obtained through this feature importance. So what is the feature importance? The philosophy of feature importance is that if you have a predictor that is, if you shuffle the value of the predictor, then it's just noise, right? And it should have no association with the outcome. And if a predictor is very strongly associated with the outcome, then shuffling it should make the prediction much worse. So the philosophy of feature importance is that I want to know if feature X is important or not. So I just shuffle the value of X and see how much drop there is in the prediction accuracy. The bigger the drop is, the more important this predictor is. And this drop in the prediction accuracy is going to be scaled by its standard deviation. And this prediction accuracy is also going to be evaluated using the out-of-bag samples. So it's free from that overfitting problem. And sometimes you may even see a negative feature importance. It means that shuffling one predictor actually makes your prediction better. That may be the case if you have two very strongly correlated predictor, and by removing one of them, you make the other predictor stronger. So in that case, the one that you remove, if you shuffle it, it will actually give you an increased prediction accuracy. So you may see very useless or even not helpful predictors having negative feature importance. But the bigger, the better. And alternatively, a predictor's contribution can be measured by the average decrease in impurity. So remember when we do the tree split, we try to find the predictor that decreases the impurities the most. And a predictor may appear in 100 of the trees in the forest, and you're going to average the drop in impurity over all of the trees that contain this predictor. And this average decrease in impurity is going to be the larger the better. So the feature importance can be obtained using this importance function. If you have continuous outcome, it will just have one column for this is the drop in MSE, this is the drop in purity. I think the first is the feature importance. The second is the average drop in purity. So there are two different ways of measuring the importance of each feature. This is the feature importance when you shuffle that predictor. This is the average of impurity drop over all of the trees. And for the categorical outcomes, for example, here we have two categories for the outcome. You will have feature importance for each category. So when you shuffle one predictor, it's going to change the accuracy of prediction for each class. And that's recorded here. So shuffling for example, shuffling, where is it? This one. This is the number of HIV partners, HIV positive partners. So if you shuffle this one, it's going to have a big impact on the positive, the misclassification for the positive cases. But it has a very small impact on the negative cases. For this one, if you shuffle it, it will have a big impact on the classification accuracy for both classes. And this is the decrease in prediction, the average decrease in accuracy over all of the trees. So it's also the bigger the better. This one is the most important one. And if you inspect them, this is tabulating that variable positive or negative against infected or not. And you can see that for all of the patients who have a positive value for this, they are HIV positive. So that's why this variable has a larger feature importance. And the next one is, I think I picked this one. This is a positive value for both, but it's not that big. If you tabulate them, you can see that it's not super informative, but it still has the right direction. So this 1/14 is going to be larger than this over in the sum. So it's an informative predictor. And for this Y example, the biggest one comes from the color and the proline. And when I plot the alcohol level versus those two predictors, you can see the linear or nonlinear. I don't know what trend, but there's a trend. So that's how you can visualize the important features chosen by the random forest. Unfortunately, you don't know the direction of the impact. So whenever you find an important one, it's better to visualize it and see where the direction is. And I guess that's all for today. It's a long day.
For the negative importance, the one you talk about, like features that might be correlated. And so track on how to interpret those.
Yeah.
They're important, but in a negative direction.
No,
They just
they're not,
become
they're not important, they're not helping. So by including them, you're actually overfitting your model and making the out-of-back prediction worse.
Right. So this would be a nice way to check whether your model is actually overfitted.
Mm,
By looking for those features that are like negative.
this is saying that I'm throwing a lot of garbage into the training of the random forest.
Yeah, so then you wouldn't check those out. Would you redo your model without those predictors?
Well, that's another question. So that's basically saying that I'm using one trick to shrink down my set of predictors and then using another trick to estimate the effect. That is cheating. It's not exactly cheating, but you need to quantify every time you apply a specific trick, there's variation, the randomness involved in there. You need to account for that randomness.
I guess the question is, you know how when you are designing your model, you don't want features that are highly correlated to be included in the model, right?
Right.
That is the kind of idea I'm talking about.
I see.
How does it apply here?
So by looking at this output, it's possible that the reason why these are all garbage is because they are correlated. So one way of doing it is to aggregate them into some score and when you aggregate them, you do it model free. You do it without looking at the infection labels. So for example, for this research study, they actually just pick a few of them and add them up as the behavioral risk score. And another way of doing it is to take principal component of all of them. Take the first two components and you shrink down them from 22 to 2. And when you do that, you are not looking at your labels, so you're not cheating. Mm-hmm. That's feature pre-processing and very useful for good models.